Hey there, everybody. So we're going to keep going here in Chapter 7 and look at trig integrals. Let's get started then. So it turns out that there's some common combinations of sines and cosines, tangents and secants, or cotangents and cosecants that happen all the time in calculus, and we have to learn how to deal with those. So here's just a few examples I just kind of pulled from the homework. If sine is odd and cosine is even, or sine is even, cosine is odd, so we're talking about the powers here. They could be both even, or here's a tangent and secant combination where they're both even. And these all have related but different techniques. So let's jump in and see an example. So just looking at it, we don't really know what to do. But you might be thinking use substitution because the derivative of sine is cosine. And that's actually what we're going to use to solve it. We're going to take one of these cosines and pull it out separately here. And the reason we're choosing cosine is because it's an odd power. So if we pull one of them out, we'll have an even power left over that we can turn into sines. And that's what we do. So this is a Pythagorean identity here. So you should have most of your basic identities memorized by the end of this section. So I go over some of them. And there's other ones that you might need. So make sure you have a trig cheat sheet handy while you're doing the homework, or just memorize a few of the identities that you see over and over again in this section. So we turn all the cosines into sines, and then we can distribute this through. So sine squared times 1 is sine squared times sine squared is sine to the fourth. Now it's a u substitution. We just make u equal to sine. Du is just cosine, right, with a dx. So this is a pretty straightforward substitution. This just becomes u squared. This is u to the fourth. This whole thing is du. Do the integral. It's real easy. And then plug sine back in. So most of the problems we're going to see in this section look more or less like this one. Some of them have different rules, different identities. But usually you're trying to identify which of these powers can we manipulate to turn one into the other. So this is the general rule. So in this section, I'm doing the examples first because the rules are pretty abstract, so I think it's better to see the examples first. So here we're saying n is odd. It doesn't matter what sine is. This still works even if sine happens to be odd as well. All we're looking at is the cosine term. If this is an odd number, then we just let n equal 2k plus 1. And then for this, we set aside one factor of cosine and turn the rest of the cosines into sines using the Pythagorean identity. So we rewrite the integral like this, pull out a cosine. This is basically what I did in example 1. Turn these into sines, right? So all I'm doing is sort of factoring the product here. This is cosine to the 2k, so it's cosine squared to the k. Inside, I can replace this with 1 minus sine squared, and then we just make the substitution. So this is just a general sort of abstract recipe for how to use this technique. But I'll give you an example of each of them. Every time we learn a new technique, there'll be an example. And it works if the power on sine is odd as well. It's exactly the same technique. The only difference is that your derivative of cosine is going to be negative sine. That's the only thing that changes. So if we let m equal 2k plus 1, we set aside one factor of sine, turn the rest of the sines into cosines. So pull out a sine here. Turn these signs, so it's sine to the 2k, so it's sine squared to the k. Use the Pythagorean identity, make it 1 minus cosine squared. And then we just substitute u equals cosine. And the derivative, again, will be negative, right? Because the du will be negative cosine x dx. So if sine is odd, use this. If cosine is odd, use the one we just saw in example 1. But they're very, very similar. If they're both odd, then it doesn't matter which one you use. So let's see an example when neither one is odd. Here they're both even, and it's a definite integral. So there's no way to do a u substitution here because we need a single power of sine or cosine. So the technique we're going to use here is we're actually going to split out a cosine squared, and so this is 4 and 1/4, so 4 times 1/4 is 1. I want a 4 in here, so I need to put the 1/4 out front because it still has to multiply together to be what we started with. In this trick, we're going to use these double angle and half angle identities. Again, if you have them on your sheets, you can look them up, but you're going to have to use these identities to do the problem, so you might as well keep them handy. So we have this rule that says cosine squared is really this. We have another rule that's going to relate to sine x cosine x. So all I'm doing here is pulling this exponent to the outside. 2 squared is 4, sine squared is sine squared, cosine squared is cosine squared. So I'm just factoring it backwards, sort of. Then this is actually sine squared of x. Sine squared of 2x. This is the half angle. And then this 1/2 times this 2 goes away. And we still have 1, 2 left over from the square. Right? So when we squared this 2, this whole thing converted. This whole thing is just sine squared of 2x. So it's just 1/2 times 1/4 is 1/8. This 2 went away. And again, if you're not sure, you can start at this step and go this way, and you'll see that it works out if you go up. So it's beginning to look like a u substitution problem. So before I do that, I'm going to split it into 2 integrals. This one over here will in fact be a u substitution. But I have to do more with this one. And all I did is just distribute this. Right? Because this is a product. And so you can distribute integrals through products and sums like this. Right? It's basically the distributive property. So sine squared 2x times 1. This whole integral is this one. And then this whole integral with this part is over here. So I had to kind of cook this up to get rid of this plus sign. Now it's 2 integrals. So now I'm going to keep going further, and I'm going to use the rule that says sine squared of u, just for any variable, is 1/2 times 1 minus cosine of the double angle. So we actually use this double angle thing twice. Over here, again, this is going to be a u substitution. So now we're ready to actually do both integrals. And here's the half angle identities. I just put them in the notes for you. Okay. Oop. So I kind of put that like in the middle of the example, just to show you that when you're doing this stuff, these are the there's like the little reference guide for what you want to use. And I used all of these actually. Right? If you look back at the previous slide, I basically used all of these, right? Here's cosine squared. Here's sine squared. Here's 2 sine x cosine x. So I used 3 of them. And that's what normally happens, right? 2 sine x cosine x is sine of 2x. right? So here, this whole thing just became, because the whole thing was squared, so the whole thing just became sine of 2x quantity squared, which we write that way. So, so that's what I used on the previous slide. Let's keep going with this example. So we left off at the bottom. And I'm going to further simplify. So there was a 1/2 out here. I brought it to the front. And I'm ready to do both of these integrals. So this first integral is really easy. This is just going to be like a real basic u substitution. This one's a little bit tricky for a u substitution. So I kind of like wrote out how we're going to do it. So it's a definite integral on the u substitution. This one, we don't actually have to do the u substitution. We can just see that the antiderivative of cosine of 4x is 1/4 sine of 4x, right? Because the chain rule gives us a 4, so we need to divide by that 4. It's a little harder to see over here how that works. If you can do it in your head, though, that's totally fine. You're allowed to do it that way. You don't have to show this work for u substitution. And some of you might want to show work for this one. I'm not saying one is better than the other. This is just how I chose to do it. Okay, so this one, we're done with the integral. This one here, we changed the bounds, 0 to pi. That should be pi. Sorry about that. I'll fix it in the notes. That should be this pi. But what we see is that sine of pi is 0. So this whole integral, these bounds just become 0 to 0. And this 1/2 goes here to be a 1/16. So we have a rule from Calc 1 that says any integral from a to a is automatically 0. You don't have to actually like work it out. This is just a rule. This one over here is 0 because the lower limit is 0, right? So we have 1/16 pi minus 1/4 sine of 4 pi. Well, sine of 4 pi is 0 as well. So a lot of this stuff just becomes 0 and just goes away. Right, so pi minus 0 plus 1/16 times 0. Almost all this goes away. You just get pi over 16. So if you wanted to do this part up here with 2 different u substitutions, that'd be fine. If you wanted to just do this in your head, that'd be fine as well. It's really up to you how you want to set these bounds on a u substitution problem. But you get the hint, right? And again, I put the little reference sheet back here, right here. So this is where you have the identities. So just make sure you keep those handy, because you're going to use them to do problems when both powers are even. All right, now we're going to look at secants and tangents. For this type of integral, set aside, this is when n is even. Set aside 2 factors of secant, turn the rest of the secants into tangents using the identity secant squared is 1 plus tangent squared. So again, we're saying that n is even, so secant is to the 2k power. Pull out a secant squared. And you can see that it just factors into this. So we have a secant squared on the inside to the k minus 1 power. And just turn those into tangent squareds. And then substitute u equals tangent x. So the reason we have to do this is because if it's a u substitution, derivative of tangent x is secant squared x dx. So you need to have that derivative sitting there. So here they're both even, but that's okay. This rule is just for secant even. It's all right that they're both even. What happens to tangent doesn't matter. So as you can see, we pull out the secant squared. We turn the secants that are in the square here, we turn those into 1 plus tangent. Now I have a square here, and I need to FOIL. So I went ahead and just did all the arithmetic on this. I FOILed this and then multiplied through by tangent to the 4th. Right, because this inner product here is 1 plus 2 tangent squared x plus tangent to the 4th x. And I just multiplied it by tangent to the 4th. So I got this whole thing make the substitution u equals tangent. Du is secant squared x dx. So that works out real nice. These all just become u. The integral's real easy. And then plug tangent back in and you're done. So that's when secant is even. Next, we're going to look at a different example. This is when tangent has an odd power. The reason we do it this way is because the derivative of secant is secant x tangent x. So we need 1 power of secant, 1 power of tangent. So for this type of integral, set aside 1 factor of secant, 1 factor of tangent. Turn the rest of the tangents into secants using the identity. So here we're just saying that tangent needs to be odd. It doesn't matter if secant is odd or even, so I'm not even addressing it. Factor out 1 tangent here, 1 secant here. All of these tangents, this group here, I'm turning into secant squared minus 1. This is to the 2k power, so it's secant squared minus 1, and then this whole thing to the k power. This secant stays the same, this stays the same, and this tangent I put way over here at the end. And then we substitute u equals secant x. So pretty straightforward stuff. What we're going to see in the next example is not one of these. I trust that you can do one of these. But we do need to prove this formula, because when we do this kind of thing, or when we have secant to an even power, when we have secant to an odd power, we see this a lot. So obviously this is to an odd power, right? Secant to the first. But we're gonna do this. I'm gonna show you how to do this integral, and then we're gonna do another odd secant integral and show you how it works. So this is just a bunch of algebra tricks. So the first thing you do is you multiply by secant x plus tangent x over secant x plus tangent x. This quantity is equal to 1 because it's a number divided by itself. Then we just distribute. You take this secant, distribute it across the top. Now if you look at it, you can see that up here we have the derivative of that, and here we have the derivative of that. So this is actually a u substitution, where u is just secant x tangent x, and du is just the derivative of both of those. And it works out real nice. This whole thing just becomes 1 over u du. So if you're not seeing it right away, just pause it and find it. Here's u, here's du. So everything just plugs right in. It's just natural log of absolute value of u plus c. And then you plug u back in and you're done. So I recommend memorizing this. Because you will see it a lot. Anytime you have secant with an odd power, this basically pops up. And that leads us to the strategy when this happens. If this is even and this is odd, there's no nice way to do it. You can always try integration by parts. And then this tangent formula we proved a long time ago. We just proved this formula. As you may recall, we also proved this in section 6.2, so this might look familiar. And we proved the tangent formula also back in section 6.2. But most people know this integral by now, because this one was just u substitution. So this formula was actually proved in section 4.5. But we've seen this integral twice. We saw it once as a derivative. I just showed you as an integral. So hopefully that's nice and locked in. And you're going to be using it a lot. So let's see how we do integral of secant cubed. Well, we pretty much know what we need to do in terms of factoring it. But we're actually going to use integration by parts. I know that's not usually the first thing you think of, but it turns out that it is really the only way of solving this. So we're splitting it into secant and secant squared. We know the derivative of secant, and we know the antiderivative, right, the integral of secant squared. So it actually works out really nice that the values are all given to us, right? We already know all this stuff. So it's uv, right, uv minus the integral of v. So v here is just tangent. Du is secant x tangent x, so it's just this times that, and so I just distributed and got a tangent squared out of it. And then looking at this, now we have odd power of secant, even power of tangent. So we got to be clever. So we're going to further break this thing down. And what happens is we actually get a trick, as you're going to see. Tangent squared is secant squared minus 1. We're going to distribute this secant x now. So we have secant cubed x is secant x tangent x minus secant times secant squared is secant cubed x dx plus secant x. We just saw how to do this integral. We're done with this section. And this is what we were trying to show to begin with. So all we do is just add integral of secant cubed x dx to both sides. It's going to cancel it on this side, and it's going to make 2 of them over here on the left side. We already know, we already computed that integral, right? That was example 4. Divide by 2, and you're done. So you can see that these problems are starting to get trickier and trickier as we go down the road in chapter 7. And that's really what happens. Once we start getting into integration by parts, it gives us ways of solving integrals that we didn't have before. And we're going to start picking up more and more formulas. And at some point, you just want to start memorizing the formulas. Because if you have to compute these live every time, it's going to take you too long. So just do your best. You'll see a lot of the same stuff over and over. And hopefully you get enough practice. So there's one more type of problem we want to see. And this is called product identities. So in Trig, you saw how to use these identities down here. We're going to use them to solve problems with integrals that look like this. And you just use the corresponding identity. So if our integral looks like this, just use the sine times cosine one. If it looks like this, use the sine, sine, and this, use the cosine, cosine. You don't have to memorize these identities. If these are on a test, I'll give you these. So here we have sine of 8x cosine 5x. You can see that that's this first type. So we're going to use this identity. 1/2 sine of a minus b plus sine of a plus b. So 1/2 sine of a minus b plus sine of a plus b. That's it. And what ends up happening is that it works out really, really nice. Pull the 1/2 to the front. 8x minus 5x is 3x. 8x plus 5x is 13x. Pretty nice. Those are really easy integrals to do. Again, these are use substitution, but you don't actually have to show the use substitution. You just got to recognize that the chain rule is present. And so you're just dividing by what the chain rule would give you. And that's basically it. Distribute, simplify a little bit, tack on a plus c, and you're done. So any problems you have in the homework or on a test that look like this will be solved using one of these identities. Alrighty. Well, that's it for this section. As usual, if you have any questions, you can post on the discussion board or email me. And that's it for this video, and I'll see you next time. Bye-bye.